In this video, we're going to look at finding the limit of a function analytically. And by that, I mean we are going to solve the limit of a function using limit laws that we can derive. So here for this first one, the limit as x approaches -1 of x to the fourth minus 3x times x squared plus 5x plus 3 is what we're trying to find. And let's use our limit laws to do this. Well, first, by the product law here, or product rule, we have that the limit, this limit here is equal to the limit as x approaches -1 of x to the fourth minus 3x times the limit as x approaches -1 of x squared plus 5x plus 3. And again, that was using our product rule here. Okay, let's continue on. This is equal to, and now we're going to do several rules. We can separate this into limit as x approaches -1 of x to the fourth minus the limit as x approaches -1 of 3x. How did we get to this? We can split this up using our difference rule. And this is all times the limit as x approaches -1 of x squared plus the limit as x approaches -1 of 5x plus the limit as x approaches -1 of 3. Okay, and again, what do we do here? Well, we just did our sum rule to separate our limits across, or distribute our limits across this sum. Well, this is, let's look at just this step right here. This is the limit as x approaches -1 of x all raised to the fourth by our power rule minus 3 times the limit as x approaches -1 of x. This is our constant multiple rule. We can pull the constant out front times, and then here we have a power rule again. So limit as x approaches -1 of x all raised to the second power now. And then plus 5 times the limit as x approaches -1 of x plus the limit as x approaches -1 of 3. Okay, now what are each of those? Now we can actually plug everything in. Limit as x approaches -1 of x is just -1. So this is -1 to the fourth power minus 3 times limit of x as x approaches -1 of x is again -1. All of that times limit as x approaches -1 of x is -1, so -1 squared. Plus 5 times -1 again, because same thing, limit as x approaches -1 of x is -1. Plus, and then limit as x approaches -1 of 3 of a constant is just that constant. So I get 3. So -1 to the fourth is 1 minus, plus 3 here, times, that's 1 plus, plus a -5, so it'd be a -5, plus 3. So we get 4. 1 minus 5 is -4, plus 3 is -1, so 4 times -1, or in other words, -4. Now, what we may notice here is that we could have just plugged in -1 into our original function up here. We just did that. -1 to the fourth minus 3 times -1 times -1 squared plus 5 times -1 plus 3, right? That's exactly this step right here. So we could have just plugged in -1 into our function. So at this point you might be thinking, well, why didn't we do that in the first place? And what is the whole point of a limit if we can just plug it in? Well, it turns out we can't plug it in all of the time. There are special situations where we can plug it in though, plug in our value though, and that makes the calculation a lot simpler. So let's write down a couple of those situations. So if p of x is some polynomial, so what is a polynomial? That is an expression of some form similar to this, or is an expression of a function that is equal to this. Let's see, a naught. So a n through a naught here are all constants. We have a polynomial. Then the limit as x approaches some constant c of this polynomial p of x is just p of c. So we can just plug in c into the polynomial and evaluate that polynomial at c, and that will be our limit. So that's nice. So for polynomials, we can just plug it in. Then also it turns out if p of x and q of x are polynomials, and q of c does not equal 0, so the denominator is not 0, then limit as x approaches c of p of x over q of x is equal to p of c over q of c. All right. So again here, if we have a rational function, then we can just plug in c as long as the denominator does not become 0. If the denominator becomes 0, then that's a problem, because this would be an undefined value over here, and we have to find other ways to deal with that. But here is our other way to deal with that. This next thing that we're going to write down. When we discuss limits, we only care what happens near the x value that we are approaching. We don't care what happens at that x value. So, in particular, if f of x is equal to g of x everywhere except possibly at x equals c, then we get that the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. So those limits will be equal as long as those functions are equal everywhere around c. So we don't care what happens at x equals c. Maybe these functions are not the same there, but as long as they're the same everywhere around it, then those two limits are equal. So let's go ahead and see why this might be useful via an example. And we kind of already saw an example in a previous video, but let's make it a little bit more clear here. So let's do an example here. And that is to find the limit as x approaches -3 of x squared plus 3x all over x squared minus x minus 12. Notice, if we plug in x equals -3, we get -3 squared plus 3 times -3 all over -3 squared minus -3 minus 12, which is, this is 9 minus 9 all over 9 plus 3 minus 12, which we get 0 over 0, which is indeterminate. What does that mean? Well, we'll talk about this later in the semester, but essentially, all right, we don't know what this is. We can't divide by 0, and especially when we have 0 over 0, we have a problem. So we can't solve our limit here. So what can we do? Well, let's use what we just previously wrote. So let's start with our limit as x approaches -3 of x squared plus 3x all over x squared minus x minus 12. What is this equal to? Well, let's just factor this numerator and denominator. And when we do that, we can factor out an x in the numerator to get x times x plus 3 in the numerator. And the denominator factors into x minus 4 times x plus 3. Okay. Well, we notice that x plus 3 over x plus 3, well, those can cancel. And we get this. But why do we get this? Why do we know we can say equality on these two limits? Well, this function is equal to this function everywhere except x equals -3, right? Because x equals -3 is not even in the domain over here on the left. But on the right, it is. So these functions are not equal, but they are equal everywhere except x equals -3. So by our previous theorem, these two limits are equal. Right? We didn't prove that previous theorem, but we did state it, and it is in fact true. And now, what can we do? Well, this right-hand side, we don't get 0 in the denominator anymore, so we can just do direct substitution. So we can just directly apply, or directly substitute in -3 here. And so we get -3 over -3 minus 4, or in other words, -3 over -7, or 3/7. So in fact, we have our solution. All right. And that is it for this video.